Hello friends, today we're continuing our study of AP Precalculus using Brian Passwater's materials, and we're on topic 2.3. All right, 2.3 is just talking about the different types of functions and focusing in a little bit more on exponential functions, what they look like, how they work, limit statements, etc. So there are three common functions in math, and I would say in physics as well when I teach physics: linear, quadratic, and exponential functions. Even in AP Physics C, at least, we do see exponential functions when it comes to topics like drag and a few other areas. So it's good to be familiar with it, and there are other applications as well. And you see what they look like, right? Linear is where it's a direct relationship with x, quadratic, x squared, and exponential is when x is in the exponent of some base, right? And so A represents, so in this, right, A represents what we call the initial amount. I should be writing this. Because when x is equal to 0, then A times B, B just ends up, the whole thing ends up being 1, right? And so that's the value of the function when x equals 0. So that's giving us the y-intercept, you could call it. And B represents the base, also known as the common ratio. That's the thing you're multiplying by each time as you go. Okay, and so exponential functions can do two things. They can either grow or they can decay, depending on what the base is, what the common ratio is. If the common ratio is more than 1, then you're multiplying by something more than 1 every time, and so it's just going to keep growing. If you're multiplying by something less than 1, then every time you multiply, it's getting smaller and smaller and smaller and getting closer to 0. Okay, and so the end behavior for exponential functions, end behavior is either going to be positive infinity, negative infinity, or approaching an asymptote, right? And if there's no translation up or down, then that asymptote is going to be 0. And that's what we have here, right? So the limit as x approaches positive or negative infinity for an exponential function equals 0. Again, assuming there's no translation up or down. We looked at translations a little bit at the end of Unit 1. So keep that in mind. So here's some samples, right? They want us to write the limit statements. So the limit as x approaches negative infinity of a times b to the x, right? Because this is an exponential function. This is what it looks like. It's concave up. And by the way, exponential functions never switch concavity. They're always concave up the whole time or concave down the whole time, depending on what's in front of it, right? If it's a negative initial term or a negative initial value, it'll be concave down. If it's a positive initial value, it'll be concave up. Okay, so for this one, as we go to the left, the limit as x approaches, so we're going to negative infinity way out there. So this gets closer and closer to 0. Never actually reaches 0, it's an asymptote. And then the limit as x approaches positive infinity of this function a times b to the x equals infinity. It's just going up to infinity. All right, for this one, on the left, the limit as x approaches negative infinity of a times b to the x equals, right, so again, as x is going farther and farther to the left, y is going farther and farther down. So this equals negative infinity. And then the limit as x approaches positive infinity, so as you go out to the right, of a times b to the x equals 0. Right? It gets closer and closer to 0. Okay, so now we're looking at a function where we have some values in there. 5 is the initial value. So if this were on a graph, it would be crossing the y-axis at 5. It's positive, so this one's going to be above the x-axis, right? But notice that the ratio, the common ratio or the base, is a fraction. It's something less than 1. So as you're multiplying, if you multiply by 2/3 again and again and again and again, what's going to happen is you're going to get closer and closer to 0. The exponential function is going to be decreasing. So we call this a decay, exponential decay formula. And so it's going to look kind of like this. So the limit as x approaches negative infinity for g of x, it equals infinity. And then the limit as x approaches positive infinity, g of x equals 0. Right. Okay. Example 2. For each of these, determine if the exponential function is increasing, decreasing, and concave up or down. Okay, so for this one, for a, we would say that it's certainly concave up, right? And it's decreasing, right? The value is just getting lower and lower as you go to the right. B is concave down, right? And this one is also decreasing, right? It's going more and more negative, which we would call decreasing. And then for C, this one, so what's it going to look like? Notice it's positive. The initial value is positive. And for the common ratio, or the base, is more than 1. So this is going to be growth. So this is concave up and increasing. Oops. Increasing like that. Example 3. This question asks us to figure out if this is linear or quadratic or exponential. Okay. So if we look at the differences, so between 3 and 5, this is a difference of 2. Between 5 and 9, this is a difference of 4. Between 9 and 17, that's a difference of 8. And then 17 and 33, that's a difference of 16. And so notice that the difference each time is being multiplied by 2. Now, 5 is not 2 times 3, and 9 is not 2 times 5. But we are seeing that there's a difference there of that the differences are being multiplied. So what this is, it's actually an exponential function that's been translated. We're going to learn later on how to translate exponential functions vertically and horizontally, stretching, compressing, all that kind of thing. But for now, all we need to do is to be able to recognize that this is an exponential function based on the difference of the output terms. So simple lesson, nice and quick. Don't forget to like and subscribe.